Okay, we are very pleased to have Dr. Rayan Saab give a talk in our 1W seminar today. Rayan now is an associate professor in the Department of Mathematics at UCSD, and he is also a member in the Halishi Global Data Science Institute at UCSD. Before that, Rayan was a visiting assistant professor and a Benton postdoc fellow at Duke University, and he completed PhD at the University of British Columbia in 2010. Rayan has broad research interests. For example, Rayan is interested in the sparse and low-dimensional representation of high-dimensional data, and he is also interested in complex sensing and related errors. He is also interested in the digitization of data and in developing and analyze quantizing approach for both oversampled and compressed sampled signals and so on. Today, Rayan will talk about algorithms for quantizing neural networks. Your turn.
Thank you, Longshu, and thanks to all the organizers for the invitation. It feels great to be on the other side of the introductions. Today I'll be talking about algorithms for quantizing neural networks. And this is joint work in parts with Eric Leibrand, who is a former PhD student, with Johannes Mali, with Jinji Zhang, who's a current PhD student, and Ishuan Zhou, who was a former undergrad, very talented at UCSD. So it makes sense to just very briefly spend a couple of minutes talking about quantization, just to give a sense of what kind of issues come up when you think about quantization. So first, quantization is a process by which parameters, measurements, or samples that normally would take on values in the continuum, so they could be real numbers, are replaced by elements from a finite set. And you might do that for a variety of reasons, including analog to digital conversion, compression, or other things. And the challenges that you usually have to think about when you're thinking about quantization can be pretty broad. So you might be thinking about lower bounds. So what is the limit of what can be achieved when you do quantization? How much error, how low can the error get? And usually you need things like approximation theory to figure out lower bounds. You might also be interested in tractable algorithms. You want to get as close as possible to these lower bounds with algorithms that run in a reasonable amount of time. And of course, you want performance guarantees on these algorithms. So you can imagine the tools that come into the game: approximation theory, probability, optimization, and so on. And in the mathematical literature, examples of areas in which people have worked on quantization include, quantizing band-limited functions, with work by people like Debussy and Devore, with Sinan, who's with us now, and others. And similarly, in the linear algebra of finite frames context, there's been work on that, compressed sensing, and so on. And today, I'm going to focus on something slightly different, which is quantizing neural networks. This is an area that's relatively new, at least in the mathematical side of things. There are lots of algorithms that have been out there for a few years that deal with quantizing neural networks, but they tend to be developed more with practice in mind. So they seem to work well in practice, but you don't really have any theory justifying them. With a few notable exceptions. I've listed some of them on the slide, and today we'll talk about some algorithms as well. Great. So I won't spend really any time convincing you that large machine learning models and neural networks have been pretty remarkable in the last few years with what they've been able to do. What I will do instead is just spend another minute or so on how quickly they have been improving in terms of performance and how quickly they have been growing in size. So this chart just shows you time on the x-axis, and it shows you the accuracy in classifying images from ImageNet over time, and the green curve is showing you the best models over this time. So you can see that the algorithms in the last 10 years have gotten so much better at doing things. You know, they were getting 60-something% accuracy 10 years ago, and now we're hitting something like 91% accuracy. And this is with, you know, classifying hundreds of classes. So 91 is not something necessarily to scoff at. And while this is great, the flip side is that it's coming at a cost. So you can see that the best model from 2022, at least up till now, has something like 2.1 billion parameters. So that's a function with 2.1 billion parameters. They train those parameters, and then they get this 91% accuracy with that. And you can see that all the top performers are in the order of billions of parameters. Not only is the number of parameters high, but also the number of flops needed to run these models. It's naturally also high because you have to touch these parameters to compute with them. And so you end up with also billions of flops to just apply the function. So ideally, you'd like to make these things smaller. Now, the other thing that I'll mention is that about a year and a half ago, when I looked at similar numbers, you know, the analog of this chart, the best models were a little bit worse than this. You can kind of see where they were, but the number of parameters was, I mean, I would say significantly smaller. So you were looking at something like, still a large number, something like 400 or 500 million. Now you've gained an extra 1 or 2%, but you've quadrupled the size of the model. So we're paying for this accuracy with size, at least so far. And that was just image processing, image classification. So if you looked at natural language processing or other types of things, well, 2019, you had something like 8 billion parameters. 2020, you're looking at 175 billion parameters. 2021, 530 billion parameters. So obviously, that's a lot of disk space, a lot of compute that's being used to work with these models. So a question that's motivating our work on quantizing neural networks is, can we reduce this computational load? Can we reduce this memory burden when we're working with an already trained model? So somebody hands you a neural network that you're perfectly happy with, and you would like to take this network and reduce its size while maintaining its performance. So why would quantization do something like this? Well, if you think about these parameters, they're essentially something like 32 or 64-bit floating point numbers. And if you were able to take these numbers and replace them by 1 or 2 or 3-bit numbers, then you've reduced the size, the storage size of this object by a factor of 10 or 30. And not only that, but also in principle, implementing these in hardware and computing with them would be much cheaper, because multiplying 3-bit numbers is a lot cheaper than multiplying 64-bit numbers or 32-bit numbers. So the questions that come up are things of the type, can you even do this? If somebody hands you a function, can you replace its parameters by quantized parameters and still be able to approximate it well? And under what conditions? Can you construct such an approximation in a reasonable amount of time? Remember, you're dealing with 500 billion parameters or so. So if you're running some exponential algorithm or polynomial algorithm, you're completely out of business. Can you obtain theoretical guarantees for these types of things? And can you promote additional properties? So maybe you want to attack the problem from 2 directions. You want to quantize, but also you want to sparsify. So set a lot of the weights to 0 and still maintain performance. So can you promote such things? Okay, so those are the questions we'll try to answer with a number of different algorithms. But let's set up some notation first. I'm going to denote by capital 5x my neural network. It's going to be a feed-forward neural network that is essentially a composition of affine and nonlinear functions. And we do this L times for L layers. Each nonlinear function, as is the norm in the literature, is a component-wise nonlinearity, for example, the rectified linear unit. And these affine functions, I'm going to write them as matrix vector multiplies. we're writing them as the transpose of what we're usually used to, because our goal is to quantize the weights. So the weights are the object of interest for us. And of course, there are these biases. These are in principle affine functions rather than linear functions. And the dimensions are for each layer are just going to be denoted by NL. So the Lth layer will take an input of size L and output something of size L plus 1, NL plus 1. Okay, so one quick simplification that's rather standard. I'm going to ignore the bias, and I'm going to justify ignoring the bias by looking at the observation that something like X transpose W plus B transpose can be written as just a linear function in one dimension higher. So we're embedding it in a one dimension higher space, and we end up with just a matrix vector multiply that looks like this. So if I just look at the new matrix W with a row concatenated at the bottom, I can think of this as my new matrix of weights. And now my goal is to replace this new matrix of weights with a quantized object Q. Great. So our approach is going to be data-driven. And in fact, we're going to talk about 3 algorithms that are loosely related today and some variations of them. And what's going to drive them is data. So I'm going to assume that somebody hands me a matrix X of training data. And this training data looks like this. Each row is a training data point. It lives in N0 dimensional space. And I have M of these training data points. Somebody also hands me a pre-trained neural network. They're happy with it. It looks like the form we just discussed. And they hand me a quantization alphabet, or more generally, the size of the quantization alphabet. So as an example, you might quantize things to -101, or some constant times -101, or more generally, larger alphabets. And as I mentioned, the goal is to replace all the weights in the neural network by quantized weights from the alphabet, so that the error at every layer, for instance, is small. Now, obviously, what you would like is at the end of, you might not care about these intermediate steps in principle, because all you care about is that the function at the end approximates the original function. But as a means to that end, you might basically say that if I am able to, at every layer, approximate the behavior of the original function, then it stands to reason that at the end, I'm going to be able to approximate the behavior of the function. So this is where this comes from. It's a first step in a series of steps that we're going to use to simplify the problem. Okay, so we've decided that we want the error to be small at every layer. So it makes sense to look at the first layer first. And if I looked at the first layer first, I would see that, well, the Frobenius norm can be just simply rewritten as a matrix vector multiply, like we discussed earlier. So I have my matrix of data times my matrices of weights and quantized weights. And that's just a matrix times a set of columns, and that's just the sum of things. So it's a Frobenius norm. It's the sum of the Euclidean norms squared of this matrix vector multiplies. This basically means that each one of these neurons better approximate, the error associated with each one of these neurons better be 0. So in other words, if I go ahead and I just try to quantize each neuron individually and make this error as small as possible, then the error on the layer will be as small as possible, and I win. In other words, I don't have to worry about the sum over neurons too much. So this means that I can focus on a single individual neuron, at least theoretically, and then just apply the algorithm to all the neurons in parallel. Which is my long story to say I'm dropping the indices J that index which neuron you're working with. So we've reduced the problem from having to work with the full layer to having to work with an individual neuron. Now, just staring at this equation, you might think, okay, this is now a simple problem. Except that what you would like to do is come up with a vector Q that is in some sense optimal. So you would like it to minimize over all possible choices of let's say plus or minus 1, this particular error? Well, in addition to the question, how do I solve this optimization problem? There's the question, even if I could solve this optimization problem, is this error guaranteed to be small? So is this an exercise worth pursuing? And there are some answers in the literature that you can lean on by making connections to discrepancy theory. So we look at the special case where the alphabet is a simple one, just -1 and 1, and where it's even a simpler problem than the one we're trying to solve. So you're actually just trying to approximate 0. So x times w is 0, and you're trying to approximate, you're trying to quantize this 0 with an alphabet of -1, 1, so that x times q is as close as possible to 0. Doesn't get, in principle, simpler than that. So the observation here is that, if you had fewer columns than rows, then looking at an orthonormal matrix, it stands to reason that xq's norm squared is just equal to the norm of q squared. And because we're working with plus and minus ones, this thing is going to be equal to n naught, and that's less than m, but that's not very close to 0. That's large. So what about more generally? Well, more generally, there's a universal constant, c. This is a theorem from the 80s by Spencer. So there's a constant c, so that for any collection of vectors, x1 to xn, that live in Rm and are in the unit ball, there exists a choice of -1, 1 bits that you can assign to q, and you end up with the infinity norm of x times q being bounded above by a constant times log m. So this is telling you that something is achievable. The error in an L infinity sense can be bounded above by c log m, and it's an existence result. Now, on the flip side of this existence result, there's a conjecture, the Komlós conjecture, which basically tells you that the best you can hope for in some sense is getting rid of the log factor. So you can get the error to be something like c in the infinity norm rather than c log m. And the implication of that is that when you looked at L2 norms, which is what we're trying to do, you would like the error would be bounded by something like c root m. So this is a conjecture. We don't know if it's achievable or not. Now, there's been progress on the conjecture and on constructions that hope to accomplish it. And there are plenty of results across the last few decades. One important one is by Banaszczyk in 1998, and it basically is a non-constructive result that tells you that you can get this infinity norm to be something like c times the square root of log m. So not quite a constant, but not too bad either. And the result is non-constructive. And more recently, there's been some work where you try to construct algorithms that achieve these tasks, but you end up needing a polynomial complexity, because you're either solving an SDP or an optimization problem of some type. And we'll have some algorithms that also are going to end up being polynomial, but then we'll also have some algorithms that are linear. I'll talk about those momentarily. So the challenge here is that these are good, but you can't really afford to run an n to the 6 algorithm on to quantize weights when you have billions of them. And similarly, you would like to not use cubic complexity algorithms. Okay, so we answered the question, can you quantize it and get a decent approximation error? Now the question is, because of the existence of these results, now the remaining question is, can you do it in a reasonable amount of time? So we're going to address this one step at a time in some sense. And we start with kind of an intuitive approach. And this intuitive approach is based on a two-step procedure. We're going to solve an optimization problem, and then we're going to do basic scalar quantization. So let's see how this might work. Well, we're going to be motivated by kind of a nice, simple lemma, independently of the problem we're working with for a second. So suppose somebody hands you a nice matrix, m by n, fat, and it's in general position. And they tell you that they're solving this optimization problem where they minimize the L infinity norm subject to something like B equals AZ. Now, the minimizer, the Z star that solves this optimization problem, has an interesting property. The interesting property is that if you looked at the set of indices on which the minimizer achieves the infinity norm, you're going to find that the cardinality of the set of these indices is greater than n minus m plus 1. So in other words, if you were looking at the solution, most of the n, if n is much larger than m, for example, most of the entries of the solution are going to be plus or minus the infinity norm. And then some few entries are going to live between these plus or minus infinity norm entries. And geometric interpretation is relatively easy to get. If you're minimizing an infinity norm, then you're basically inflating an L infinity ball until it hits a linear or a linear constraint, and it's going to hit on a face or a low dimensional face of this cube, and then by staring at this picture for a few minutes, you can convince yourselves that it stands to reason that the cardinality of the things at which the infinity norm is achieved is going to be given by n minus m plus 1. So this is a three-dimensional picture, and in this case, n is 3, m is 2, and you end up with two of the entries achieving the infinity norm. Okay, so that lemma seems unrelated, but it gets us thinking about an algorithm. So the algorithm is something like this. Now, we're going to replace our arbitrary matrix A by our data matrix X, and we're going to replace our B by X times W, where W is a vector of these weights that we're trying to quantize. So how are we going to do it? We're going to solve an L infinity norm optimization problem, get a vector W hat, and the constraint we're working with is that our W hat has to satisfy that XW hat equals XW. So somebody hands you a neuron, it has some weights. You're going to take those weights and replace them by another set of weights that gives you the same product X times W, but where the new weights have small infinity norm. And as a bonus, we get this property that the optimizer is basically between most of the entries of the optimizer, if n0 is larger than m, are going to be either negative c or c. So in some sense, they're already quantized to negative c and c. All we have to do is take all the remaining entries, which basically are fewer than m, and quantize them to either negative c or c, or if we have a richer alphabet, to things in between. So that's essentially all we're doing. We're optimizing and quantizing. So we first solve the optimization problem. Everything that takes on the values negative c, c, we keep. Everything in between, we just do simple scalar quantization. We round them to the nearest element in the alphabet. And then it's easy to analyze this simple algorithm. And you end up with results and corollaries of the type that I'm going to mention. So the paper has many more results, but this is just an example result. Say you have n0 larger than m, you have weights in this L infinity ball, say, and you have data that is Gaussian. And then you construct using optimize and quantize, then with high probability, your relative error is going to behave like the square root of m log n times infinity norm of w divided by 2 norm of w. Now, this is a little bit difficult to interpret, so at first glance. So let's basically just interpret it in some generic case where the vector W has no particular structure. It satisfies the property that the 2 norm is something like the square root of n times the infinity norm, which a random W would satisfy. And if you just plugged in the numbers in that case, you would notice that the relative error is now something like square root of m log n over n. In particular, this means that as you have more and more parameters in your layer, your relative error decreases. And what is hidden in the squiggly sign is basically the size of the alphabet and how small the gap between elements of the alphabet are. So if you had a finer and finer alphabet, you would have, of course, a smaller and smaller error, which makes sense. So I see some things in the chat. Okay, no problem. So this was kind of a first approach to attack the problem. It has some nice properties, and it has some issues that would be nice to address. So what are the pros? The error decreases with the size of the alphabet. This is something that you would expect, and it's nice to see that it happens. The error decreases with overparameterization, at least the relative error does, as we just saw. And I basically described to you the proof strategy in that one slide. So the proof is pretty elementary, and it has no complicated parameter tuning. You just hand me the weights, I run this algorithm, and everything is done. Now, in reality, there's a little bit more complication. You still don't have to do any complicated parameter tuning, but you have to connect the fact that you're not working with a single weight, not working with a single neuron, but rather working with a layer. So you would like all these infinity norms to be somehow aligned with each other, rather than to solve each one of them separately and get different negative C's and C's. But it turns out that you can solve a slight modification of this optimization problem. And with a slight modification, you get all of them aligned and you get those same error bounds. So in the interest of clarity, I just didn't present that. Now, what about the cons? Well, the computational complexity is the computational complexity of solving this linear program, the L-infinity minimization problem. So in some sense, it's polynomial in M and N, depending on how, if you're using an interior point method and you want to get close to the solution. And in the paper, we also have results that replace these optimization problems with algorithms. So, sequential algorithms that get close to the optimal solution, and then you basically have control over the computational complexity. Our algorithm also would relax some assumptions, so it wouldn't need the general position assumption either. But maybe more importantly, or equally importantly, is it's hard to do proofs for multiple layers because our results really depend on, or getting quantifiable results really depends on knowing something about the structure of the data matrix X. And once you feed the data to multiple layers of the network, it's very difficult to get a set of reasonable assumptions to work with on the data. So that's the challenge here. Okay, let me look at the question in the chat. Do you control the flow of input data in any way? You mentioned iteratively optimized and quantized and repeat. You can influence by participating. Yeah, so here we're just basically feeding the data in, getting an output. We measure the output, and then we run the optimization algorithm. That's basically it. So we have access to the network, to the original network itself. So we know what the intermediate activations are at every layer. Okay, so let's switch gears and talk about a different approach than this optimized and quantized approach. Now what we're going to try to do is reduce the computational complexity, but keep the nice results, the nice theoretical results. And here, the game is the following. We're going to observe that a matrix vector multiply is really just a weighted sum of columns of the matrix. And as such, if I think of this as a sequential kind of cumulative process, where to get to the full sum, I'm going through the partial sums first, then a reasonable greedy algorithm is to say, can I pick these Qs so that I get the partial sum to be approximately equal to the true partial sum? So I get to pick these Qs sequentially in such a way that the partial sum up to step T is as close as possible to the original partial sum up to step T. This is why we're calling it a greedy approach. You're making the greedy choice at every step, but it's also sequential. So the algorithm, just to put it in a form that's amenable to analysis, would look something like this. Start with some vector that accumulates all the errors. And of course, before you start, you set it to 0. And then at every step, pick the bit, pick the Q that minimizes the sum of the previous error plus the current error. And then update the state variable that tells you how much error you've accumulated so far. So that's just a mathematical description of the algorithm that I described maybe a minute ago. And it turns out that by just doing something as simple as completing the square, you can, let me slow down, you can replace this argmin step by a very concrete step that just relies on rounding. So again, just by completing the square, it turns out that this quantization business ends up being just a scalar quantization, a rounding to the nearest element in the alphabet of the scalar quantity. What is the scalar quantity? It is the current weight plus the inner product of the current column vector with your previous error and then appropriately normalized. And then you update the state variable. So I promised you that this would have lower computational complexity than solving an optimization problem. Let's take a look at its computational complexity pretty quickly. You're running an algorithm for n naught steps because that's how many columns you have. At each step, all you have to do is round a scalar. So that's not expensive. And the scalar itself is computed as a vector-vector multiply. So that's, and each vector is in m-dimensional space. This costs you O of m operations. Updating the state variable costs you O of m operations. So the total complexity is m operations n times, which is mn. Now remember, the size of your data matrix is mn. So if you were just reading the whole data, it would cost you mn, and this algorithm is a multiple of that. So it doesn't get too much better than this, unless there was a way for you to reduce the size of the data and still obtain good results. Okay, what about theory? Well, this is a theorem you can prove. It's a relatively general theorem, and then we're going to apply it to some special cases. So the theorem is the following. Somebody hands you a distribution D. So think of this as the distribution of columns of X. And this distribution has some nice properties. So what are the nice properties? The nice properties are that the expectation over vectors drawn from the distribution of this quantity is greater than some lower bound. So it's bounded away from zero. So, I mean, it's easy to see that this quantity is a cosine or a cosine squared. And it's the cosine squared of the angle between your randomly drawn vector and an arbitrary vector u. So if you could guarantee that for any choice of u, the cosine squared of the angle of this randomly drawn thing has an expectation bounded away from zero by s squared, then you're happy. And second of all, you would like that the norms of these vectors are bounded almost surely. Now, in reality, you don't really need almost surely, and we're going to get results for things like Gaussian, so it won't be a problem. Once you have these two nice properties, you can guarantee that if you have an alphabet with step size delta, so for example, you know, your alphabet would be negative delta over 2, delta over 2, the step size between those two elements is delta. And suppose that you draw your matrix from this distribution. Suppose further that your weights that you're trying to quantize are bounded above by some number. Then when you quantize using the algorithm that I just described, you're going to get that the probability that the error is small is large. How do we see that it's large? Well, this S is something between 0 and 1 because it's a cosine. So this is just a number that gets better or worse depending on S. But importantly, the probability depends on N, and the error depends on this ratio R over S. So this seems a little bit obscure until you start plugging in numbers for distributions that you care about. So let's do exactly that. Let's plug in numbers for distributions that we care about. For simplicity, let's just work with an alphabet that looks like negative 1, 0, 1, but the theorem would hold for any alphabet that was that had a kind of nice arithmetic structure. And then suppose that you draw your matrix from a Gaussian distribution with normalized columns, and your weights were in the unit infinity ball. Then by applying the theorem, you would get that with high probability, the L2 norm squared of the error is bounded above by m log n. So for those of you with a good memory, you'll remember that this was pretty much what we saw when we were working with the optimize and quantize algorithm. We saw something like an m log n. And this result would hold not just for Gaussians, but for things like Bernoulli distributions. It would also hold for things that you might be interested in later layers of the neural network, like Gaussian mixture models, where you could argue that a neural network that was trying to do classification would, towards the end of the layers, separate the different classes into Gaussian clusters or clusters that could be modeled as Gaussians. And in that case, looking at X as being drawn from something like this would still work out and give you results of this type. And also importantly, this theorem works when X is more structured than just being a matrix drawn from a distribution, but if it has the structure that would be implied by a convolutional neural network. So I won't get into the nitty-gritty details of that, but it basically follows relatively easily from the analysis. Okay, so let's maybe assess these results for a moment. We basically said that the L2 norm squared was m log n. So the L2 is something like square root of m log n. We had previously seen from the discrepancy theory part, the lower bounds part, that we had this conjecture that the best you could do is basically get the infinity norm of the error to be bounded by a constant, in which case the 2 norm of the error would be bounded by a constant times the square root of m. And what we're getting instead is square root of m times the log of n. So we're paying an extra log n factor as compared to the conjecture, but that's about all the costs we have. Now, of course, our result is not as strong as the conjecture because we're assuming that the matrix is drawn from nice distributions, whereas the conjecture is saying for every x, this holds. But still, this is good, a good sanity check. So just another corollary to look at the relative error. The relative error is going to look exactly like the relative error of the optimize and quantize. So it's going to decay in the case of generic weights, like the square root of m log n over n. What about the case that X has low rank structure? Will the bounds be better? That is indeed an excellent question, Longshu, and perfectly timed. For example, if X is drawn from a d-dimensional subspace, so it has this kind of low rank structure, then you replace M, which is the number of data points, by D, which is basically the dimension of the subspace. So the bounds would indeed be better. Now, an interesting open question is if there was even more structure than something like a low dimensional subspace, but maybe the data was drawn from a manifold or a union of manifolds, can we say anything? And if we cannot say anything, can we modify the algorithm to be tuned to that structure? So that's a very interesting open question for this algorithm. Okay. Let me also say that another kind of result associated with this greedy algorithm is that you can modify it a little bit to enforce this compression even more. And the game here is you're going to try to push as many bits to be quantized to 0 as possible, while still maintaining the performance. So there's a long justification that you could go through for the algorithm, but then what you end up with an algorithm and it's surprisingly intuitive. So let me just tell you what the algorithm is. You basically, instead of quantizing the quantity that you were quantizing before, so before you didn't have this weird S lambda, right now you have it, and you were just quantizing the scalar quantity that we talked about earlier. Well, if you wanted things to be pushed towards 0, maybe it makes sense to do something like a soft thresholding operation or a hard thresholding operation to push the quantities towards 0 first and then quantize them. Now, that's completely intuitive, but as I said, it also has a nice, reasonable theoretical justification. Now, for those of you who have not seen these operators before, you could have a soft thresholding operator here or a hard thresholding operator. A hard thresholding operator basically says anything that is less than less than absolute lambda, I'm going to set to 0. And anything that in absolute value is greater than lambda, I'm going to keep unchanged. And soft thresholding does more or less the same thing, except it pushes things down so you get a continuous function. So these are natural operations, and they're natural things to think about when you do quantization, if your goal is to enforce sparsity. And remarkably, you can prove that you basically don't pay a high price for sparsification. So in particular, say you have a Gaussian, something drawn from a Gaussian, but all the other results that I mentioned in the previous slide would also work. Then you can guarantee that with high probability, the error looks exactly like the error that we saw before. This 2 norm of W would look like the square root of n, and you'd get the same relative error business. So where are you paying for this lambda? You're paying for the lambda and the constants. So Song Ki is asking, what does lambda represent again? Lambda represents basically a threshold in the soft thresholding operator. So soft thresholding would take inputs. This should be a straight line, but soft thresholding would take inputs represented on the x-axis and gives you outputs represented on the y-axis, and it sets everything in between negative lambda and lambda to 0. So that's what lambda represents. It's sort of how aggressively you're setting things to 0. So Mark is asking, what is the dependence of lambda and the constant? And I should just write this down. The dependence is going to be something like this, delta plus lambda. So delta was the step size of the alphabet, and lambda is this, and our dependence is linear in this lambda. Now, the thing that is harder to get a hold of is how does lambda affect the sparsity? So it's reasonable to say that as lambda continuously grows, you're going to get more and more zeros, but it's more difficult to say what is the percentage of zeros that you're going to get as a result of increasing lambda. And we'll do a quick experimental kind of investigation of that when I talk about the numerics in a few minutes. Okay. So quick summary of this approach. The error decreases with the size of the alphabet as before. It decreases with overparameterization as before. The computational complexity in broad terms is minimal in the sense that it's Mn. And if we had a low dimensional structure that was linear, like a low rank matrix, then you would end up with Dn instead. And the algorithm can be easily modified to promote sparsity, and you get nice results, nice theoretical results. And we'll see that we also get nice practical results. Now, the cons are that it's going to be, again, difficult to come up with proofs for multiple layers because it's hard to guarantee that these nice properties about the matrix, the cosine squared being bounded away from 0 and so on, are going to hold after 7 layers of neural network, linear, nonlinear processing. So that's where the difficulty in handling multiple layers is. And we'll try to overcome it with the third approach now. And I'll be quick with the third approach. So the third approach just says, well, instead of relying on randomness in the data, let's inject randomness into the algorithm. So what we'll do is, rather than quantize things deterministically, we'll quantize them stochastically. And in particular, let's do this with an example so we make this more accessible. Say you're trying to quantize pi, just the number pi, to an integer. What the stochastic quantization will do is it'll say, we're going to quantize pi to 4 with probability 0.1415, blah, blah. And I'm going to quantize pi to 3 with probability 1 minus that. And as a result, the expected value of quantizing pi is going to be pi, even though I never quantize to pi. I always quantize to 3 or 4 with varying probabilities. So this is stochastic quantization. It has a lot of use in things like compressed sensing and other areas. And it leads to a modification of our algorithm where we kind of marry the two ideas from the previous two approaches. So we're going to call this randomized greedy path following. And because this is going to work with arbitrary layers, let me just spend a a few seconds describing the notation. I'm going to call phi the output of the neural network up to layer L, so the function that applies the neural network up to layer L, and phi tilde, the function that applies the quantized neural network up to layer L. And then our weights at that layer are going to be W. We're going to have an alphabet that I'm going to vaguely say is large enough. So now we're paying a price rather than having an alphabet that is negative delta, delta. The alphabet has to be sufficiently large to handle what we're going to do. And I'm just going to set the matrix of activations, basically the data pushed through the network up until layer L, and call it Y. And then the quantized version of that, I'm going to call Y tilde. So as far as we're concerned, this just means instead of thinking about X being data, think about Y being the data pushed through L layers of the neural network. And now we'll solve an optimization problem, which is basically saying, find me the smallest coefficient in infinity norm so that these should be flipped. This should be Y tilde W equals YZ. But basically the game is, I want to replace the weights of the original network with new weights so that the quantized one and the unquantized one give us the same output. So I'm not thinking about quantization at all. I'm just thinking about replacing the weights of one network to match the output of the other network. So that is what this optimization problem is doing. And the reason I want to minimize the infinity norm is because these are the new weights that I will quantize. And I want them to be bounded in infinity norm so that the size of my alphabet doesn't blow up. So then what algorithm do I run? Well, same algorithm as before. Now, instead of working with X, I'm working with Y tilde because that's my quantized network up until now. And instead of working with the weights of the original unquantized network, I'm working with these W hats that I backed out of the optimization problem. Instead of doing deterministic quantization, I do stochastic quantization so that I have some randomness to analyze the algorithm. And then I just update my state variable. So if I run this algorithm, then we can prove a theorem. And the theorem basically says that with probability 1 minus gamma, your L infinity norm error, so this is nice because we are getting now an error in L infinity instead of L2, which means we can back out the L2 error, but we can also get pointwise bounds. And this error is just something that looks like a square root log factor, which is nice, times the maximum of the column norm of Y tilde. So this is a little bit, this is something that you basically have to have control over depending on the properties of your neural network, because Y tilde is the output of the network up until a certain number of layers. So it depends on things like Lipschitz constants of the neural network and so on. But the nice thing about this is that you can also leverage it. So I didn't present this here, but you can also leverage these types of things to get results that look exactly like the results we had for the non-random stuff from earlier. So we don't really lose anything on the subset of cases that we already have results over. And then we get new results for subsequent layers with this randomized algorithm. Okay, so quick recap, and then numerics, and then that is basically it. So the quick recap is that we now have proofs for multiple layer neural networks by using this randomized algorithm, but we paid for it. And the price we paid is the computational complexity. We need to solve an optimization problem now at every layer to get there. Now, in practice, you actually don't need to solve the optimization problem. You can work with the network as is, because these L infinity norms turn out not to blow up. And so you don't need this artificial control, but at least to get the theory to work, you need to do that. And very related to this is that you need finer control on the alphabet size. Okay, some quick numerics. So I won't spend time on the setup because we already talked about it. I'll focus on the middle algorithm, approach 2, and then make some comments about approach 3. So So this is the result on AlexNet, which is now an old neural network, but it still has 60 million parameters. Over here, we see batch size. So that's just code for what M is. So as the number of data points increase, as M increases, you're training on more and more data. And then you're testing on a separate data set. You're validating on that data set. And you're looking at the top 1 accuracy, which is what we saw in the early slides, but also the top 5 accuracy, which is basically asking the question, if I looked at the 5 highest classification scores, is the true class represented in those top 5? And then, of course, the accuracy is going to rise if you relax your definition this way. So this is top 5 accuracy, this is top 1 accuracy. And the different colored graphs are basically telling you what happens if you use 3 bits, 4 bits, or 5 bits to quantize. And you can see that as you get more and more data, your accuracy improves. And as you use more and more bits, of course, your accuracy improves. But the nice thing is that just by increasing the number of data points, you can get really close to the original accuracy with a small number of bits. So that's AlexNet, which doesn't have too many parameters, which is another way of saying it's not highly over-parameterized. This is ResNet, which has 23 million parameters, but behaves better. And we see the same type of performance. More data gets you better results, more bits gets you better results. And it seems like you can converge to the original accuracy just by increasing the data size, but we ran into our own computational bottlenecks because we don't have the large cluster of computers that Google does, for example. Okay, this is VGG16 now. It's a bigger network, and I just want to put this result to highlight the sparsity business. So here we're 138 million parameters, so arguably more over-parameterized. Our accuracy is without sparsification is what you're seeing here. So again, by just increasing the batch size, you get closer and closer to the original accuracy. By increasing the number of bits, you get closer and closer to the original accuracy. But now on the right, we're also exploring the role of sparsity. So we take one of these things over here, and we set a lambda, and we increase this lambda. And in green, we plot how the sparsity is increasing. So we just simply are observing how many coefficients are 0. And as we increase lambda, we go all the way up to something like 70% of the coefficients are 0 in the whole network. And the remaining ones are quantized to, now I forget if it was 4 bits or 5 bits. So that's the green curve. It just tells you that the sparsity is increasing monotonically, as you would expect with lambda. And then, of course, you care that the error doesn't collapse as a result of that. And indeed, it doesn't. It actually decays pretty gracefully. So as you increase the sparsity from something like 10% to something like 70%, the error only drops a little bit. And depending on your application and depending on how much you care about sparsity versus performance, you could pick up point on these trade-off curves that work. So we were very pleasantly surprised by this, because it shows that you can compress further than just by quantizing, and that doing one thing doesn't preclude doing the other. Okay, so we're almost done. I just want to say a few words about open problems and future work, because there's a lot that is still open. So you would like faster algorithms with proofs for multi-layer quantization. You'd like to weaken randomness assumption on the training data and use non-stochastic quantization methods, because stochastic quantization is a little bit more expensive than non-stochastic quantization. You'd like to get generalization bounds for data models like manifolds and things like this. You'd like to account for things that people do in practice, like retrain after each layer, or tricks like this, because they boost the performance. And you'd like to think about variations that promote compression even more than just sparsification and quantization. So maybe changing the architecture of the network. And you'd like to account for things that people do in practice more directly. So we worked with Frobenius norms and L2 norms and L infinity norms, but people optimize for other loss functions. And that's really the norm in practice. So you'd like to see that you can work with things like this as well. These are some references, and thank you for listening.